This video shows how you can actually come up with poor MPC performance indices. We have established that a performance index comprising quadratic terms is likely to lead to easier optimizations and smoother outcomes. This video introduces some typical, or you might call them naive, performance indices based on quadratic terms and shows how these relate to common sense but what the outcomes might be if you are not careful. First of all then, let's look at what the errors might be. If I have, here you'll see past time less than 0, future time greater than 0, then I can very quickly work out what the predicted errors are in the future. So I'm going to put a number of arrows here, and these arrows could correspond to EK plus 1, EK plus 2, EK plus 3, and so on. So in this diagram you can very quickly see what the predicted future errors might be. And what I want to do is I want to make these errors small. That's my objective. A typical and logical performance index then would be something like this. J equals the sum from 1 to n of EK squared. Because if I minimize J, this implies that EK is small for all values of K. So the smaller J is, the better the expected tracking performance, and that makes common sense and everybody's quite happy with that, and we're using quadratics of the error, which again makes good engineering sense. The one thing that I've not discussed here is what's an appropriate choice of n. You'll notice I'm only summing the errors over n steps. Now this particular issue is discussed later because there's lots of subtleties and misunderstanding in this, and we don't want to get confused at this point, which is just an overview video. What you're going to see, however, is that a performance index like this is actually not a good choice. You might say, well, it seems to make sense, minimize the square of the errors, great, but a simple J like this may well lead to control decisions which are very poor. Here's an example. If I choose G like this, z to the minus 1 minus 1.2 z inverse, oh, that should be z to the minus 2, all divided by 1 minus 0.64 z inverse plus 0.8 z to the minus 2. Now, my job is to minimize the given J. So I want to choose a future input sequence to minimize J. So what I'm essentially doing is saying minimize over u future J. Now what you'll find is that you can find an input sequence which makes all the future errors 0. And the way you do that is by inverting the plant. So if I write that u equals 1 over g times r, where r is the target, then that will imply that j equals 0. And you might say, great, that's a really good controller. I've made all the errors 0. Haven't I done a good job? Well, let's have a look. If I use this particular process here and I invert the plant, this is what the input would be if the target was a step. And when you plot it down here, what do you see? The input is divergent. So though the errors, the tracking errors, may seem to be 0, because the input signal is becoming divergent, there's going to come a point where the input saturates and everything goes to pot. So what do you conclude? A cost based just on tracking errors in general gives you poor input signals, and so it's not a very wise choice. We've got a different example here, not so bad as the last one, but just to demonstrate the point. So what you can see here is an input signal which is very, very large. Here's the input signal that comes when I just minimize the tracking errors. You can see the input is very poor. Because you're focused so much on the tracking errors, you've made no account at all of what the actuation is, and so the optimization has said if the actuation needs to be very large, then so be it. There's no penalty on that, and so it's made the input as large as it needs to be. Now in this particular case, you'll look at the tracking performance, which is over here, and you can see the tracking performance is very good. And you might say, great tracking performance, but you haven't looked at the consequences on the inputs. And therefore, this form of optimization or performance index tends to be ill-advised for most systems. So, a performance index linked to the predicted output errors might make sense, but we can't do it on its own because we're also concerned about actuation. Too much actuation causes fatigue, is expensive in fuel, requires over-specification of valves, etc., etc. And so it's logical to also penalize the input signal. Therefore, you end up with a performance index a bit like this. You can see I'm not only penalizing tracking errors, but I'm also penalizing the magnitude of the input. I'm saying large inputs are not good, so let's penalize the square of the input. And again, you might say, yeah, that seems to make good engineering sense. I've got no problem with that. Let's see what it does. Unfortunately, this also gives us problems. This performance index will not work. So while it seems to include what you want, it includes tracking errors, it includes input activity, if you now look at the steady state analysis, you will see that this performance index is ill-posed. Okay, it's not well thought through. There's my performance index, the sum from 1 to n of ek squared plus lambda uk squared. Now I'm going to assume that I'm at steady state. So YSS equals G USS, that's what's going to happen at steady state. And I'm going to say what happens if I put in the steady state values. So I minimize over the steady state input, E the steady state errors, plus lambda times the steady state inputs, and I substitute in what I've got here, YSS equals GUSS. So I'm minimizing over USS this function here, and that will tell me where the system will drive me in steady state. So if I'm in steady state and I minimize this, I should get the same U. And of course what you find is that clearly USS cannot be equal to R over G. Because if that was the case, then in this optimization, this term would be 0, and this term would be not equal to 0. And it was very easy for a mathematician there to realize that this simply cannot happen for this quadratic. And so therefore, the optimum cannot give you YSS equal to the target. And therefore, it's ill-posed, because if you use this performance index, you cannot converge to the target that you've chosen. And so the summary here is this sort of performance index cannot simultaneously drive the tracking error and the input to 0. So this is not a good choice of performance index. So in summary, while the use of quadratic performance indexes is the most common choice within the literature and tends to result in smooth and robust designs, there are things you cannot do. You cannot be naive. So you cannot choose the function simply to be a square of the tracking errors, because if you do this, you'll tend to find that the control actions are far from desirable. You cannot simply add in a square of the input actions to reduce control activity, because if you do this, you result in a steady state offset because the performance index is ill-posed. The next video will actually look at performance indices that work, that deliver what you really want.